Okay, here's a typical reaction of an alkyl halide like you might see, 1-bromobutane reacting with sodium ethoxide. So in organic, that ET is just ethyl, so this is ethanol, right? 2 carbons, like that. Ethoxide, conjugate base of ethanol. That is a strong nucleophile and a strong base, right? If you go back to that video where I talked about nucleophilicity and basicity, it's a lot of charge on that oxygen atom, small, highly charged thing, good nucleophile, good base. You're going to see 2 products show up in this reaction. The first one is the SN2 product that we can maybe now predict, where this ethoxide comes in, sort of reacts from the backside, kicks out bromine, and we end up with that ether as a product. Again, I have a new carbon-oxygen bond. It came in, forced that bromine out, SN2 reaction. I also see an elimination reaction, we'll call the E2, that'll give me this alkene. So just like the SN1 and E1 are paired, so we can also think of the SN2 and E2 as kind of a pair. So how is this working? So the 2 means bimolecular. And what I mean by bimolecular is that 2 molecules are coming together in the rate determining step. Like the SN2 reaction, the E2 reaction is a 1-step reaction. Okay? Here's what's happening in that step. My base, this is a base. Now I don't really care about its nucleophilicity, I care about its basicity. My base is going to take a proton from the carbon next to the carbon with the leaving group. Draw the arrow like that. These electrons in that bond are going to fold over, and then my leaving group is going to leave. So at the end of all this, what I have is bromide by itself as a leaving group, an alkene, and in this case, ethanol, because my base took that proton. Again, elimination reaction. Elimination reactions give alkenes as products, and this is bimolecular because 2 molecules are in the transition state. Like I said, the SN2 and E2 reactions kind of go together, so we can compare them in our little fact sheet that we've been working with. So they both need a good leaving group. Again, we are always kind of talking about alkyl halides in these cases for the most part. Just like the SN2 needs a good nucleophile, the E2 reaction needs a good base. So the nucleophile and the base show up in their respective rate laws. So they're dependent on concentration, and they're dependent on having good quality nucleophiles and bases. We can refer back to that video that I had that showed you that good bases versus good nucleophiles plot. So good nucleophiles, SN2, good bases, E2. Okay, solvents, for the same reasons, these things are pretty general when it comes to solvent, but they prefer those polar aprotic solvents the best. Again, protic solvents like water might overstabilize our base, so we don't have enough base to make it work. Substrate. So here there's a bit of a difference. For SN2, we're really worried about nucleophilicity in terms of our nucleophile sterically being able to get that backside attack and fit in there. And so steric hindrance plays a big role. The least sterically hindered it is, the better off we are. Because we're dealing with bases, and bases are just trying to take away tiny little protons kind of from the outside. They're not trying to do backside attack on a carbon. Sterics are not usually a problem in the E2 reaction. And so sterics aren't a problem, then what are we looking at? Well, we would want to get the most stable product, because usually the barrier to that most stable product is usually the lower barrier. And so in this case, we often see a selectivity that looks more like the more substituted the alkyl halide, the faster the reaction goes. So again, tertiary halide like tert-butyl chloride, too crowded for the SN2, but the E2 likes it because sterics isn't an issue if I'm just trying to grab a proton from the edge. And also, this will give me a nice many substituted stable alkene product, so that's cool. Now one thing we might not get into too much is that for the E2, you actually can do it on an sp2 reaction. You need to really force it, but there are cases where if I have some base, I can actually attack an alkene like this and eliminate, lose HBr, and get to an alkyne. So it's kind of a cool reaction that can happen. So of the four, the E2 is the only one that maybe could do an sp2 carbon if you forced it. So what about things that are good nucleophiles and good bases, like hydroxide, methoxide, ethoxide, conjugate bases of amines, of acetylids? What about those? How do I know whether they're going to give me an SN2 or an E2 reaction? Well, a lot of times we'll have competing reactions, but unlike the SN1E1, they don't share a rate determining step. They're not going through the same transition state. So sometimes we can exert a little bit of difference. But again, I don't want to give the impression that I'm always going to be able to 100% force it one way or the other way. But our first example is a good one, right? So here, if I had butyl bromide and ethoxide, could I change my reaction conditions to favor either this ether or that alkene product? And it turns out that one thing I can do is that higher heat actually pushes our system a little bit closer to, or pushes the rate for E2 faster than the rate for SN2. Why is that? Well, think of it this way. The hotter the reaction goes, the more entropy plays a role in the total Gibbs free energy, right? So remember, Gibbs free energy, delta H versus T delta S, right? Some old school 116 coming at you, right? So entropy, we can think of, don't think of entropy as disorder. That actually doesn't work at all. What entropy is basically possibility, right? So how many different ways could I arrange energy in this system, okay? And the higher the temperature gets, the bigger role entropy of the system is going to play in our overall Gibbs free energy, which again is going to dictate the selectivity of the reaction. Okay, so both of these are irreversible reactions. So we're not talking about thermodynamics or delta G naught. We're really talking about delta G double dagger. Okay, so here is one difference between these two reactions. This reaction gives me two things. This reaction gives me three things. Three is more than two, right? So think of this as like a spin-off, right? Like this show, there's sort of like two spin-offs where people can have adventures, but if I go this way, now there are three different sets of adventures that I can have, right? Like this is the Cheers bar, and here's Frasier. Oh, he's moving to Seattle to hang out with his dad. Fantastic. And then this is maybe some third spin-off. I don't know, did Carla get her own shoe? She should have. That's a lost opportunity. But the idea here is that the more things I have kind of flying apart, the greater entropy difference I have, because these three can kind of exist in more space and more energy levels than simply two things. Okay, so again, I can't always perfectly control whether something is going to go one way or the other, and that's something I'm going to have to factor in when I consider planning out my synthetic pathways. But one kind of little handle I might have is to look at the temperature of the system. Right? If I run the reaction at higher temperatures, I might increase the E2 reaction more than the SN2 reaction. I'm not saying that higher temperatures won't increase the SN2 at all. I'm saying that increasing temperature raises this more than it raises that. So now I've changed my bromide just a little bit, and I'm going to treat it with tert butoxide and tert butanol, right? So kind of the acid and its conjugate base set up there. So this is what we call a bulky base. It's those methyl groups there are going to kind of prevent it from being able to get close enough to that carbon to do an SN2 reaction. But it's a good enough base to do an E2 reaction. So bulky base is a good indication that we're looking for an elimination reaction. Just like the SN2 has very specific and particular stereochemical requirements, so also the E2 reaction has very specific stereochemical requirements. So for the E2 reaction, the hydrogen we're going to take and the leaving group that's going to leave need to be anti-periplanar. So it needs to essentially look like this, where the hydrogen and the bromine are in a straight line in a plane, and that they're kind of opposite each other. Again, why is that? It just gets back to orbital overlap, right? I want good overlap between this bond I'm trying to break and this bond I'm trying to break in order to make the new bond. So we need to, whatever we have, we need to redraw it so that the bromine and the hydrogen are on the same plane and opposite each other, anti-periplanar. And so you can check my work here. I think I've done it correctly where I've got the configuration at both of those carbons correct. But again, you can fact check me on that. So now that I've drawn my compound with my H and my Br anti-periplanar, now I can do the reaction. So base is going to come in, take that proton, again, mind the arrows. That electron pair is going to come make a pi bond. That electron pair goes with the bromine. It looks something like this. And let me tell you, I kind of hate drawing an alkene like this, right? Because sp2 carbons like those are flat. So I'm looking at the end on. That's kind of a silly way to draw an alkene. So when you draw alkenes, please draw flat alkenes with flat sp2 carbons without dashes or wedges like that. Notice that my product here is actually not the most stable product I could have gotten. Right? I probably want the bigger groups to be opposite each other. But in this case, this is the only one I can get if I need my H and my Br to be anti-periplanar. So the E1 reaction is always going to give me the most stable alkene as my major product, but the E2 reaction needs to be able to adopt this geometry, and so it might not give me the most stable alkene possible. So here we go. I've got my terp-butyl group kind of locking this into place. So my bromine is pretty much going to stay axial here. I'm using terp-butoxide and T-butanol. So that's classic bulky base E2 conditions. And this should be a good E2 reaction. But remember, which of these hydrogens am I going to take? This one, this one, this one, this one, some combination. So remember that we need to be able to assume this anti-periplanar relationship between the hydrogen we take and the leaving group. So the hydrogen I take not only needs to be trans to the bromine, but it needs to be trans and anti. And so here the only one that works is this one. All right? These two protons are axial, or these two protons are equatorial, and so they're kind of off angle from where I need them to be, right? So, and this one is cis, right? And so is this one. So what I need is anti and both axial to do this reaction. Okay, so I know that my base is going to come in from this direction, take this proton, push electrons, push electrons. So I know I'm going to get this alkene product. Again, not the most stable product I could have gotten, right? If my double bond would have been going to the other side, it would be more substituted and therefore more stable. But I need to be able to adopt the right geometry to do the reaction. And the right geometry I can only get to give me this elimination, that product, which is that product.